Good morning, students. Today I am going to discuss with you the topic of types of superconductors. Before that, we had done what are superconductors, what is superconductivity, and what is Misner effect. And superconductors are behaved as ideal diamagnetic materials. Now we will continue with this types of superconductors, right? Superconductors are classified on the basis of transition temperature and critical magnetic field. These are classified into two types: type 1 superconductors and type 2 superconductors, right? So on the basis of magnetic field and on the basis of critical temperature, I will differentiate this with the help of diagram. This is the difference. This is the graph between applied magnetic field and magnetic field produced by induced superconducting currents, right? When an external field is applied, right? This is HA is the external applied magnetic field, or you can say applied external magnetic field, and HB is magnetic field produced by induced superconducting currents when external magnetic field is applied. Means you can say magnetic field is induced by superconducting currents, right? So in case of type 1 superconductors, as we increase the value of HA, the value of HB also increases, and at some specific value of H called critical field or critical magnetic field, there is a transition from superconducting behavior to normal behavior, or we can say at critical magnetic field the material converts to superconducting state to normal state, and this transition is abrupt transition, we can say, in case of type 1 superconductors. But in case of type 2 superconductors, type 2 superconductors, we can say when HA is increased, the HB also increases, but at some particular value called HC1, this is called lower critical field, right? Here the transition goes not abruptly, transition goes slightly, or we can say it is in the lower state, or transition is not abrupt in this case, we can say, right? So this is called lower critical field, this is called upper critical field, and HC is the critical field. Means in this region the type 2 superconductors are in the mixed state, or this state is called vortex state. In this state the superconductors are behaving as a superconductor material as well as a normal material, or you can say superconductors as well as normal conductors, right? And at this point the magnetic lines of force starts penetrating at this point, right? As we increases, they are penetrating and they are in the mixed state, and at this point the superconductor is completely converted to normal conductor at this point, called upper critical field. Again I repeat the same thing. Type 1 superconductors are also called soft superconductors, and they exhibit the complete Misner effect, or they exhibit the perfect diamagnetism. That is, above critical field the specimen is a normal conductor, and the below critical field the specimen is behaving like a superconductor, and there is a abrupt transition from normal conductor superconductor to normal conductor at some specific field called critical field, right? It is also called soft superconductors, right? In case of type 2 superconductors, type 2 superconductors are the superconductors in which magnetic flux starts to penetrate the specimen at field called HC1, that is called lower critical field, right? And the specimen is in a mixed state. The specimen or the material is in a mixed state between HC1 and HC2. This mixed state is also called vortex state, and it has in this state the material is behaving as a superconductor as well as a normal conductor, right? And this type 2 superconductor is also called hard superconductors, and type 2 superconductors have a large amount of magnetic hysteresis induced by mechanical treatment, right? Solenoid wound with wire of superconductor can produce field over 100 kilotesla, we can say. So they can carry high supercurrent densities in high magnetic field and are thus of great commercial importance, right? So incomplete Misner effects occur in the region between Hc1 and Hc2, and this region is called mixed state or vortex region, right? So in this region, the magnetic flux or magnetic lines of force gradually starts penetrating the specimen. As the magnetic field is increased beyond Hc1, heavy cold worked and recovery annealed materials having high dislocation density and fine grains are used for making type 2 superconductors. And example of type 2 superconductors are zirconium, niobium, titanium, 60% niobium, 40% titanium alloy. Okay, now we will differentiate between type 1 and type 2 superconductors. The difference is that first thing is, it in case of type 1 superconductors, it exhibit the complete Misner effect or perfect diamagnetism, we can say. In case of type 2 superconductors, it exhibit incomplete Misner effect. Incomplete Misner effect means in between range Hc1 and Hc2 it is behaving like a normal as well as a superconductor, right? In case of type 1 superconductors becomes a normal conductor abruptly, means at some critical field it abruptly changes to normal conductor. In case of type 2 superconductors, it loses its superconducting property gradually, not abruptly, right, due to increase in magnetic field. This is the main difference, means it converts to normal conductor abruptly, and it converts to normal conductor not abruptly but gradually, right? In case of type 1 superconductors, third difference is that it has only one critical field, Hc. In case of type 2 superconductors, it has two critical fields, lower critical field and upper critical field, right? And next difference is there is no mixed state or vortex state in type 1 superconductors, whereas in case of type 2 superconductors there is mixed or vortex state, right? And fifth point is that it has highest known critical field is 0.1 Tesla, which is very low as compared to the critical field of type 2 superconductors, that is 30 Tesla, right? The examples of type 1 superconductors are lead, zinc, aluminium, gallium, mercury, etc. Whereas in case of type 2 superconductors, the examples are zirconium, niobium, 60% niobium, 40% titanium alloy, right? So these are the differences between type 1 and type 2 superconductors. Again, there is a topic of type 1, type 2. Okay, next one thing is there, what is critical current? Critical current, the minimum current that can be passed in a sample without destroying its superconductivity is called critical current. So if the definition appears, what is critical current? The minimum current that can be passed in a sample without destroying its superconductivity is called critical current, right? So this is the definition of critical currents. Now next topic is London equations. So what are London equations, or electrodynamics of superconductors? Okay, London theory is based upon the two fluid model. Two fluid model means we consider normal electrons as well as super electrons, right? So it is based on two fluid model, according to which a superconductor can be composed of both normal and superfluid electrons, right? So Maxwell equations are unable to explain electrodynamics of superconductors. The London brothers in 1985 derived two equations called London equations. According to this theory, it is assumed that there are two types of conduction electrons in superconductors called normal electrons and super electrons, right? Normal electrons and super electrons at 0 degree Kelvin. Okay, superconductors contains only superconducting electrons, right? But as the temperature increases, the number of normal electrons to super electrons also increases, until at transition temperature all the electrons are normal. At any temperature, the sum of superconducting electrons and sum of superconducting electrons and normal electrons is equal to the conduction electron density in a material, right? So in the normal state, we can say. Okay, now consider, we will derive this thing, we will derive the London equations. London brothers had developed two equations, so our aim is to find those two equations. Now for that we consider, let Jn, Js, Vn and Vs be the density, Gn and Js be the density of normal electrons and superfluid electrons, and Vn is the velocity of normal electrons and Vs is the velocity of superfluid electrons, right? If n is the total number of electrons, then on an average n is equal to nn plus ns, right? So total number of electrons remain constant in a material, so total current density becomes J vector is equal to Jn vector plus Js vector. As we know that J is equal to nev, so J vector is equal to Enn Vn plus Ens Vs, where Nn is the number of normal electrons, Vn is the velocity of normal electrons, Ns is the number of superfluid electrons, and Vs is the velocity of superfluid electrons, right? In a superconductor, electrons encounter no resistance, means resistivity is zero to their motion. So if electric field is maintained in the material, then electrons accelerate steadily under the action of this field, right? So the equation of motion for a superconducting electrons, that is F is equal to ma is equal to ee, right? So ma, the equation of motion for superconducting electrons, if we are talking about superconducting electrons, so we take Vs as the velocity of superconducting electrons. So ma, acceleration is the rate of change of velocity, dvs by dt, that is equal to F is equal to ee, right? So E is the electric field and E is the charge. So dvs by dt, take m to right hand side, becomes ee by m, take it as first equation. So supercurrent density, we know that J is equal to nev, Js is equal to ensvs. So differentiate both sides with respect to t, dgs by dt is equal to d by dt of nev, right? So in this case, dgs by dt is equal to E is constant, ns is number of superfluid electrons constant, and rate of change dvs by dt, right? So dgs by dt is equal to ens dvs by dt, but dvs by dt is ee by m from first equation. Put this value of dvs by dt from first equation here, ee by m, e and e square, so it becomes ns e square e by m. So djs by dt is equal to ns e square e by m. This is London's first equation, which describes absence of resistance. Here no resistance is noted here, there is no resistance in this equation. So this is called London's first equation, djs by dt is equal to ns e square e by m, right? So this is the London's first equation. We will stop here. Thank you very much.